Okay, dear students, so this is Professor Varun, and today we are going to start with our new lecture series, which is for the topic thermal physics. In the old syllabus, it was the topic 3.1, and in the new syllabus, the topic is named as V1, and there is no major difference between the syllabus of these two topics. Exactly same thing. So in this video, we are going to learn two major concepts. Basically, point number one is the particle model of matter, which is very easy to understand. And the second concept that we are going to learn here is what is temperature and how the temperature is measured. What are the various scales, and we would be talking about that. Okay, so let us start with the first topic, which is the particle uh, model of matter. So we know that these are three different states of matter, and they are solid, liquid, and gas. Solid, liquid, and gas. Nothing major to note here. It's just chit chat. We're just going to talk. Nothing major to note here. So what is happening is like the particle model of the matter says that actually the matter is like whatever substance you're talking about, it is made up of particles, and these particles are having different properties based on different physical states. Like for example, if it is gas, so the molecules are having lesser interatomic forces. If it is solid, the interatomic forces are very strong. Something of that kind only we are going to discuss now. So what happens is like in the gas, what happens is that these molecules are not attached to each other at all. They are very, very far away, and these molecules are moving at some velocities in random directions. So they are moving, and they do not have like the interatomic forces are very small, but they are not zero, of course, but they are very small. So that is what is gas. But when we talk about the ideal gas, we assume that all the interatomic forces between the two atoms is zero. So the ideal gas, we say interatomic forces are zero. Interatomic forces are zero. So we are going to learn more about the interatomic forces and energies while when we will do the topic of internal energy and other, which is going to be in the next video itself. So we will learn about these things at that time. So presently you need to understand that as per the gases are concerned, the molecules and the atoms, they are not attracting each other with a considerable force. That force is quite low, and they are free to move away from each other. So they are, you can just assume that they're not connected with each other. This is what is a gas. Now liquid, so what happens in the liquid is these gas molecules, they now come together to a lesser distance, and they start influencing each other with the interatomic forces. So they are still relatively free to move, but still the density of the molecules within the volume that increases. So number of molecules are more in per unit volume, you can say. And in liquid, the interatomic forces are not zero. So interatomic forces are not equal to zero. So there are interatomic forces, they are interacting with each other, they're attracting each other. So that is happening. And okay, something about the kinetic energy, one more point. In the liquids and in the gases, the molecules are not in vibration state, like they are in translatory motion. So the molecule is actually moving with certain velocities, and all these velocities are random velocities. Similarly, even in gases, there are translational velocities. Again, random translational velocities. So they do have kinetic energy, and in a liquid also they do have some kinetic energy, but the forces are comparatively lesser. And let us talk about the energies also. In the next video, we would be going into deeper details, but I am going to tell you a bit of that even in this video. So in gases, we can clearly see that the interatomic forces are very less. The interatomic forces, like let's say there are two charges, those who are attracting each other. So we did in the case of electrostatic forces and others, that it give rise to a force between the two particles. Similarly, when there is the interatomic force, like in this case, there is no interatomic force. So the potential energy for this gas, it is tending to zero, but not zero. But in the case of ideal gas, we take it to be zero. and only kinetic energy is there, and that even translation. So the formula for this will be half mv square indeed. Okay, so this is the translational kinetic energy, okay, which is not zero there, and indeed it is considerable. But the potential energy in the case of gases, ideal gases, is zero. Now in the case of liquid, the potential energy is not zero, as well as kinetic energy is not zero. Both of them are there. Clear? But no doubt potential energy is always negative. So the potential energy keeps on becoming more and more negative as we go towards these solids. So the potential energy is becoming more negative here. The potential energy is zero. It is going to become negative here, and in the solid it is going to become very, very negative. What happens in the solid is these atoms now they are arranged in a particular array, a particular order, like this. So they're arranged in a particular order, like we can say that. So there are many types of structures, like the people, those who are having chemistry also, so they might have studied solid state. There is a topic named solid state, and in that topic we learn about many crystal lattice structures. So they are kind of like BCC is the body centered cubic, and then FCC is the face centered cubic, and HCP. So there are many kind of structures in which the solids they are arranged with each other. But the thing is, now the solid is having fixed positions. The atoms and the lattice is not able to move around in the space. In the case of liquid, they do move around, and in the case of gases, of course, they are free to move anywhere. But in the case of solid, they have a fixed position. They can't do anything. These bonds in between, like, they actually do not exist. Actually, there are no bonds there. We just draw them, but these bonds are actually not there. Instead of that, like, you can say that they are only attractive forces with each other. So much so that they act like spring. So we can assume that as if they are connected with some springs like structure here. Why I am calling them springs? You see, they have a peculiar nature. And what is this nature all about? Like, if these two atoms they are pushed together, they are brought together near to each other, they will start repelling each other. Okay, just like the springs will do. And when I would like to stretch it and I would like to break the solid, at that time they start attracting each other. They would be providing with the restoring force, the restoring force which is quite similar in nature to springs. So we can just show them here that they are actually connected with each other with springs, although there are only forces with each other. Okay, so do not get confused. We are just showing them like this. So what we want to say is that these molecules, they can go like this, they can move like this. But the atom cannot fly away. It means that in this case, potential energy is highly negative. Highly negative. But the kinetic energy, translational kinetic energy, is absolutely zero because the atom cannot move around. But instead of translatory kinetic energy, now we have vibrational kinetic energy. Vibrational kinetic energy, and these molecules are vibrating as if they are connected with each other with the help of spring, and so they are vibrating. They similar to the simple harmonic motion and all that, so they keep on vibrating. So more is the temperature, more vigorous becomes the vibrations, like that. So this is known as vibrational kinetic energy. So vibrational kinetic energy is definitely not zero. So we can clearly understand this, that in the case of liquid, we can say translatory kinetic energy is huge. Vibrational kinetic energy could be there in liquid, but the amount will be far more lesser when compared to the solid. And in the case of gases, definitely the vibrational kinetic energy will not be there at all. Because now, if you're heating up the material will be moving with higher translational kinetic energy. rather than the vibrational. So the vibration is no longer happening. It happens only in the case of solid. So this is what is happening there. And now we can clearly find like what is the total energy there, the total energy here, and the total energy here. So the total energy in the case of gases will be only and only translational kinetic energy. Total energy here will be potential and kinetic. And in this case also potential plus kinetic. But try to understand, this doesn't mean that the total energy will be more for solid. Of course not. The total energy is maximum in the case of gas because we have to give some heat energy to the solid to break the bonds and become liquid. And then we would be giving even more energy to the liquid so that the bonds break and they convert themselves into gas, which clearly means that gases will be having the maximum amount of energy indeed. No doubt about that. But in the case of gases, we can clearly see that the potential energy is zero. In the case of solid, the amount of vibrational kinetic energy increases to far much more extent. So we can say that the vibrational kinetic energy is bigger in ratio in the case of solid. Okay, dear students, so this is it.